Hello. Ooh, that is really loud. Yeah. All right, I guess we'll go ahead and get started now. So someone asked me out in the hall, they said, how do you deal with public speaking anxiety? And I said, well, I don't get that nervous, but the reality is that they teach you that the best way to deal with speaking anxiety is to imagine that the entire room is full of people that are naked. Okay, looking at this crowd, that's an image I do not want to try and purge from my brain. So we're just going to be nervous and not worry about it. So, all right. So today we're going to be talking about using MikroTik for load balancing. And load balancing is one of those questions that I see a lot on the forums. And the technical support guys at MikroTik have told me as well. It's a very often asked question. And it's something that I've had a little bit of experience using lately in a couple of applications for customers. So we're going to talk about one approach today that uses something called PCC, or per connection classifiers. So we'll go ahead and get started now. So a little bit about me. First of all, I'm from College Station, Texas. Anybody know where that is? A few of you? Okay, great. Texas A&M. A&M, hey, come on now. A&M just recently entered the SEC. We found out we couldn't beat anybody in our old conference, so we decided to get beat up in a new conference. Yeah, the first game I was watching, they said, in the first half, we looked like we were going to dominate. The second half, we're already looking for a new coach. So I've been using MikroTik since about 2004. I started my first WISP in 2004 called Wixon Wireless, and we tried a lot of different technologies. We tried monowall and several others, StarOS, if anybody remembers StarOS. But what we finally landed on was MikroTik because of the power and the flexibility and the GUI and the support and all the things that go along with it. So I've been using it for about 8 years now. I recently wrote a book called RouterOS by Example, which we're selling at our table. I'm a MikroTik certified trainer, and I also teach RouterOS classes. My website is mywisptraining.com, and I also sell products under ispsupplies.com. About every third time I click the button, it actually changes the slides, so we'll see what happens. Okay, the most important thing, make sure you come and get your free t-shirt. If you don't understand the shirt, and some people that work for me didn't understand it either, so we'll be glad to explain it to you. So question number one, what is load balancing and why would I want it? Question number two for today is which method should I pick and how does it work? And I think the second part of that is the most important part. How does it work? Because we can copy and paste commands from the wiki all day long and create configurations and not understand how they work, and troubleshooting them becomes a nightmare. So let's look at how this particular method works. And third, okay, I want it, but how do I set it up? So that's what we're going to talk about today. So here's a scenario that a lot of us as providers find ourselves in. We have a customer that wants to deliver some kind of internet access to a property, whether it be a hotel or an apartment, but either due to the location in a rural area, there is either no availability of high-capacity circuits, or they simply have a budget that won't allow you to bring fiber into the location. So in this particular scenario, typically our only choices are maybe some DSL circuits, possibly a wireless connection, or even a cable modem. So in this particular scenario, one of the things that we can do is load balancing. That is, use multiple lower capacity circuits and divide our load amongst those different circuits so that we can aggregate that resource and be able to deliver decent access to the property. So question number one was, what is load balancing and why would I want it? Well, by definition, it's a process to utilize multiple internet connections in such a manner as to proportionately distribute internet access or traffic across all of those connections. Now, this distribution can either be symmetrical, meaning that we have connections that are all of the same capacity, or they can be asymmetrical. So sometimes we can get a 10 by 10 cable modem circuit and then maybe a lower capacity DSL circuit. But nevertheless, we can use any of those types of distributions and make them work for our purposes. Load balancing is also useful when the downstream bandwidth requirement to a single routing device exceeds the capabilities of a single internet circuit. So basically the same thing, just said in another way. So some of the options that are available for load balancing. First, the type of load balancing we're going to talk about today should not be confused with any of the bonding protocols, especially some of the really old school stuff like multi-link PPP or sub-packet type load balancing. Bonding, multi-link PPP, all of those require that the protocol be recognized on both ends of the connection. So if you're buying a 7995 DSL circuit, they're probably not going to be able to do any kind of bonding for you. And contrary to what I've been asked several times, you can't just simply create a bridge interface and put a bunch of connections on it. That doesn't work either. There are several methods, and when I say several, I mean a lot of methods to do load balancing in RouterOS because it is so configurable. In fact, I did a search on the wiki, and if you disregard the advertisements that came up at the top there were 88 hits on the wiki site about how to do load balancing. Now, that doesn't mean there's 88 different ways. There's only a handful of different ways, but everyone has their own concept about how it should be done within those parameters. So the first group of techniques I would call ECMP, or equal cost multipath routing, which is a per address pair type load balancing. The address pairs we're talking about here are source address and destination address, which every packet has. One problem with ECMP is it doesn't work well for certain protocols because connections get broken when the routing table flushes every 10 minutes, which is a feature in the Linux kernel to prevent DOS attacks. So your connection may be going out one of the WANs right now. You're logged into your banking site. The table flushes and that connection gets dropped. And that doesn't make customers happy. So ECMP is not necessarily the right thing to use in a masquerade or a natted environment. One of the answers to that is something called nth load balancing, which is a per connection load balancing with the addition of persistent connections, which helps solve some of those problems. I also saw a lot of different hybrid or custom scripting solutions that involve several of these different methods. There's also something a bit more complicated, bandwidth-based load balancing using MPLS and traffic engineering, or the per connection classifier, which is what we're going to talk about today. In my opinion, this is the simplest way to do load balancing. It's very effective, it's scalable, it doesn't have any of the nasty side effects of some of the other methods. It is a per address pair load balancing method. And the question now, how does it work? Okay? So I told you before, this is not going to be one of those presentations that gives you a few lines of code and you copy and you paste it and you're done, because to me, if we don't understand what is actually happening in the background, it's really hard to troubleshoot, and it really doesn't help you to learn anything. So I want to talk very specifically about some terms that we're going to use in the configuration, as well as what's happening in the background. So first of all, what does PCC do? Per connection classifiers divide the incoming data coming into the router into multiple streams and then uses routing rules to sort that traffic evenly or not evenly, depending on what we want to do, across multiple WAN connections. So if we have two balanced connections, both with the same capacity, we would probably want to distribute our load evenly. On the other hand, if we had one connection that was a fairly high capacity and one with a lower capacity, we would want to put more of our traffic on that with a higher capacity. And this is done by, one, using a hashing algorithm that sorts the traffic based upon source address, source port, destination address, destination port, or a lot of different combinations of all those things. More on that later. Secondly, we will use a packet marking scheme and a routing mark and several different routing tables to ensure that traffic flows out the connections that we want it to flow out in an even manner. So now, understanding the solution, and all of us that are familiar with RouterOS will agree that it's a very programmable, very configurable, and powerful operating system. Now, this can be a double-edged sword because sometimes things that are very powerful can have many ways to accomplish the same purpose, and that creates confusion. There are a lot of moving pieces here to this configuration, so we need to understand what is happening in the background. And again, I see the greatest success with my students and my customers if they understand the solution and they understand all the pieces that are built into the solution. So now let's talk about some terms, and some of these are very elementary for this particular group, but nevertheless, I think it's important that we all begin on the same footing. And so for those of you that have not defined these terms before, we'll do it together. And the first term is packet, okay? The packet is the lowest element on the food chain. It's the container that our data is going to ride in, okay? So think of it as a header that has directions for the packet and a payload that actually contains the data. The second term I'm going to use is connections. I like to think of the connections as the conduit through which host-to-host communications occurs. So a connection is like a pipe, and the data is going to flow through the pipe. Connections are categorized by their source and destination address and ports, and we'll see more of that in a moment. The third thing that we need to describe is the mangle facility. Mangle is a firewall function built within RouterOS that allows you to create marks that are associated with packets. It also, depending on which action you choose, allows you to manipulate parts of the packet. We can then put marks on the packets and identify them later with certain firewall rules or routes and make the traffic follow a flow that it would not normally follow. Next term is PCC, or per connection classifier. This is a function within the mangle facility, and this is what's going to do our sorting. And number 5, the routing table. The routing table is a list of rules that the router uses to determine which interface it's going to send a packet out of. So when a packet arrives at the router, it looks at the source and destination address, and then it compares those to the routing table and makes a decision where that packet needs to go. So one of the things that we can do with this mangle facility is put a routing mark on our packets and then have our packets follow a certain list of rules that are particular to that routing mark. So the first term we talked about here was packet. And I like to think about a packet like a plain old-fashioned envelope, a U.S. mail envelope, and 8 cents, that was a really long time ago. So the envelope represents the header of the packet. And if you've ever sent a letter before, you know that you always put the return address for the envelope in the upper left-hand corner, and where you're going to send it to goes in the middle. A packet is just like that. It has a source address, which is where the packet came from, the machine that sent this particular packet. And then the to address is where the packet is going to go, and that's called the destination address. So that represents the header of the packet. What's inside the envelope is the payload. That's the data that the packet is carrying. A little less graphical view here is this diagram, which shows the IPv4 header, a source address, who sent the packet, the source port, destination address, who will receive it, and the destination port. The second term is connections, and I'd like to describe connections like phone calls. And for those of you that aren't as old as me, this is called a telephone, okay? This is called the dial. It turns, it has numbers, not push buttons like you're used to nowadays. I showed my kids an old telephone like this one time, and my 6-year-old said, "Where's the send button?" Okay, so back to this. Talking about connections, we have several different types of connections. And actually there's 4: new, established, related, or invalid. So how do those overlay on my scenario here? Well, an example of a new connection is me picking up the telephone and making a phone call to some other telephone. That's a new connection. When the person on the other end answers, it becomes an established connection. Now we have two-way conversation going across the phone lines. Another scenario is I can pick up the phone, call a friend, I place the phone call, that's a new connection. As before, when he answers and we talk, that's an established connection. And now we go up to 1980, and we can make a three-way call, and that becomes a related connection. So now we basically have 3 people talking on the phone at the same time. Okay? Now, this is probably not super accurate from a networking protocol, zeros and ones kind of view, but this makes sense to me, and it's very easy to understand. The 4th type of connection that we don't really cover here is an invalid connection. Invalid connections are not useful to us in any way. An invalid connection is a connection that's not part of an established connection, but it's not the right type of packet to create a new connection. So some sources of invalid connections could be badly written software, hackers, that type of thing. And then finally, what is a SYN packet? It's the type of packet that starts a new connection. So those are the 4 connection types: new connection, established, related, and invalid. 3rd question, Mangle facility. Where do you find it? Well, if you're using Winbox, like I do, you'll find it under IP Firewall on the Mangle tab. And if you click the plus sign, you can create a new Mangle rule. Mangle rules work on an if-then principle. So if the packet matches this particular criteria that we set up, then perform some kind of action on it. On the General tab are the matchers. And here we can define which traffic we want to match. And on the Action tab, we can perform some action on it. In this case, we'll match a certain type of traffic, and we'll put a routing mark on it. Number 4, PCC. What is it? Per connection classifier is a Mangle option that sorts data into multiple streams so it can be marked and identified later. So the analogy that I use here is a number of packets, red, green, black, blue, whatever. They're in no particular order. The packets flow into our series of Mangle rules with the PCC action, and they are then sorted into streams. So chaos goes in, sorted streams with marks come out. Now, in the case of load balancing, we'll be marking those according to the number of WAN connections that we have. In this case, we have 4 connections to the internet. Where do you find PCC? Well, again, it's under IP Firewall Mangle on the Advanced tab, and it's spelled out as per connection classifier. I spoke before about all the different options that are available with PCC, both addresses and ports, both ports, and so on. And we'll talk more in a minute about which of those we're going to use. So how does PCC work? Well, I always want to know how things work. Got me in a lot of trouble growing up. I'd always take things apart. So how does PCC work? Well, it takes selected fields from the IP header, those selected fields being what we select here. And with the help of a hashing algorithm, remember that term, it converts those fields into a 32-bit value. The value is then divided by a denominator, and the remainder is compared to a specified remainder. If those 2 remainders are equal, we mark the packet. You can choose from source address, source port, destination port, or a lot of different combinations. All right, so a couple of new terms we haven't defined yet. Hashing algorithm, denominator, remainder. Where do those come from? Well, first, hashing algorithm. If you're a programmer, you already know this. But if you're not, and you're like me, you want to know what it is. So a hashing algorithm is a mathematical function that takes an input and returns an output. The output will always be the same for a specified input. So if you put A in, you always get Z out. So here's an example of a simple hash. Input times 100 equals some hash value. So if you put input of 1, you'll always get 100. If you put input of 5, you'll always get 500. So that's a very simple hash. What's the hash that RouterOS uses? I don't know, and I don't care because it doesn't really matter to me. But now at least I understand what it is. A couple of more terms that we used earlier. Numerators, denominators, remainders. What are those? Well, I looked it up because I wanted to know too. They're parts of something called modular arithmetic. Some people call it clock arithmetic, taken from the concept of a 12-hour clock. So it's represented by a percent sign, and whenever it's used in modular math, the percent sign is pronounced as mod. So to work modular math, you can think of it as how many are left over, that is the remainder, after you have subtracted the second value, the denominator, from the first value, the numerator, as many times as possible without going negative. A little cumbersome the first few times I read it, but it really does make sense. So here's an example. If we have a numerator of 3 and a denominator of 3, and we say 3 mod 3, that is equal to 0, because if you take and subtract 3 from 3, you have 0 left over. That's your remainder. Another example, 4 mod 3 is equal to 1, because if you subtract the 3 from the 4, 1 is left over. If you subtracted 3 a second time, you would go negative, and that's not allowed. And then the last one here, 6 mod 3 is equal to 0, because you take 6, you subtract 3, you get 3, you subtract 3 one more time, you get 0. So that's modular math. That's what PCC is using in the background to figure out which stream is going to be which. So modular math helps us understand also how to create the PCC rules. So if we're going to create a setup to load balance on 2 connections, 2 WAN connections, we're going to need 2 PCC rules. Now, the classifier that we picked is up to us. In this example, I picked source address because it's fairly easy to understand. That is, where did the packet come from? So the hash is going to be constructed from that source address and create a value. The other 2 settings you have to put into the PCC rule are the denominator and the remainder. The denominator is always going to be an integer number equal to the number of connections that you have. So if you have a dual WAN connection, you'll have the number 2 always in the rules. If you have 2 WAN connections, you'll always have 2 rules. Now, where it gets a little sketchy is the remainder. All you have to remember is that your first WAN connection will start with a 0. The second one will be a 1. You'll add a 1 to the 0. So if you had a third connection, what would you guess the third one would be? 2. Okay? Pretty simple. So what does this mean? The first line means produce the output of the hash function given the packet's source IP address, divided by 2, and if the remainder is 0, perform the action of marking the connection as WAN 1. The second rule, same thing, marks it as WAN 2. So we've already seen how to do 2 connections. We'll fill in the blanks with 2 and 0 for the first WAN connection, and then 2 of 1 for the second. If you have 3, this first number jumps to 3, and we go 3 of 0, 3, 1, 3, 2. The 5th question, what is the routing table? The routing table is found under IP routes. The routes determine which interface a packet is sent out in the simplest terms. They also tell the router which upstream router will be taking that packet on to its next hop. There's 2 key pieces to a route. They are destination address and gateway. We normally specify a network address here, or a subnet. Although it's legal that we could put a single host IP address here, it would give us a lot of rules if we did that. So typically the destination is a subnet that we are trying to get the packet to. And the gateway is the IP address of the host or the router that's going to get it to its destination. Now, in a typical route, there is no value for routing mark. If we're going to do this policy-based routing, and we're going to use these routing marks, this is the place we tell the route which routing table this route belongs to. In this case, I've created a route, and I've set the routing table to blue. It could be 0, it could be WAN 1, it could be whatever you want, but we'll just go with blue. One of the things that you can do now is have multiple routes to the same destination. In the case of load balancing, we're going to have multiple default routes. Each of those default routes will be in a different routing table. For purposes of our example, I have 3 different routing tables. The main routing table, which you always have, even without any route marking, a red routing table, and a blue routing table. Each of the routing tables stands alone and is separate from the others, and it has different routes in it. Using the selector in the upper right-hand corner of the route list, we determine which routes we see in the routing table. In the first view, we see all routes. In the second view, we see only the main routing table, which is where our routes typically live. In the next view, we see the red routing table, only 2 routes in the red routing table. And the last one, the blue routing table, we have 3 routes. So, quick review about these terms. First of all, packet. The packet is the container for our data. Next is connections. Remember, that's the bidirectional conduit for communication between 2 hosts. The third one is the mangle facility. I just changed my slide. Hold on. Third one is mangle facility. The mangle facility manipulates packets by matching certain packets and adding marks. The fourth is the PCC function, which divides data into streams based on those marks. And the fourth is a routing table, which is a list of rules that determine where we are going to direct the packets. Okay, number 3, I want to set it up, but how do I do it? So here's our scenario again. We have the availability of 3 lower cost business class DSL connections, and we have a single router. 1 router, many clients, and so we simulated that for purposes of this presentation in our lab using a router board 750 and a 450. In this case, the 750 acted as the service provider, and the 450 is the router that's going to be doing the load balancing. Two main pieces to this setup. First of all the basic stuff that you would have to set up on a router if you were deploying it at a location. You'll need to put on a private IP address on the LAN interface, possibly DHCP server to serve your customers. Set up a DNS server, static IP on the WAN interfaces, or possibly DHCP client on the WAN interfaces, and then some kind of firewall. This is not really part of this presentation. This is the basic stuff that you can learn through the CNA class, or you can pick it up on the wiki or the forums. What we will concentrate on is the load balancing part of the configuration, the mangle rules and the routing rules. So here is how we physically connect our router. We have 3 WAN connections that will connect to either 1, either 2, and either 3. We won't use either 4, and either 5 is going to be our WAN connection to our clients. This is what I described to you previously in number 1, the initial setup that you have to do on any device to deploy it at a customer location. You have to set up IP addresses. Possibly you're going to use DHCP for your WAN addressing. Masquerade rules to masquerade the traffic so it can hide behind the public IP. And DNS client and DNS caching. So that's covered elsewhere. This is the part we're going to focus on. Mangle rules to mark our connections. Mangle rules to associate those routing marks with the packets based upon connection marks, and routes to send traffic out the WAN connections in a predetermined manner. So, we have an exception that we have to deal with here. When we start telling packets where to go and bypass the main routing table, packets don't follow their natural flow. So we have to account to that. So any subnet for which the router has an IP address configured on it is called a connected network. So if you have two routers connected together, like your load balancing router connected to your provider's router, they're going to have IP addresses on the same subnet. This means that if we use these routing marks and these special routing tables, it's possible that we could circumvent the normal flow of the packets. So instead of packets going out an interface to a local host, we may actually send them out one of the WAN connections. So the first rules we have to create are going to be called accept rules. And these accept rules are going to look for traffic that should be local to the router and allow it to follow the main routing table and not get marked for the special routing. So here's the scenario. We have a router and it's connected to 3 different networks. What we don't want to do is send packets that need to go to this network out of a different interface. We want these particular packets to follow the main routing table, and we do that by bypassing our mangle rules. There is an accept action in mangle, and what the accept action does is simply allow the packet to flow out of the mangle chain without continuing down and marking the packet. So, step 1 in the configuration is to create one mangle rule for every connected network. In this example, the only connected networks are our WAN networks. So 172.17.0.0, 172.18, 172.19. So these are the packets we're going to match, packets that should be local to the router. And we're going to use the action of accept. That way, all directly connected networks will follow the main routing table and not get routed through our alternate routing tables. This is how those 3 rules look in the command line. So you can copy and paste if you want. You notice we have 1 rule for each connected network. And this completes our 3 accept mangle rules. The next step is to create some rules that will sort the traffic into streams. We're going to use the PCC function now. We're also going to use something called the optimal mangle. In the optimal mangle, instead of simply mangling packets, we mangle connections first to mark those connections, and then we mangle all the packets that are associated with that connection. The reason for doing that is it reduces the amount of resources on the router. So the first step is identify the traffic, mark the connection. The second step is look for that connection mark and mark the routes. So this is found under IP firewall mangle. And we're going to create 3 PCC rules in the pre-routing chain. The first rule says, in pre-routing, if packets come in our LAN interface, Ethernet 5, and if they have the special connection mark of no mark, we're going to use the PCC classifier of both addresses, 3 and 0, so this is our first WAN connection. Now, several choices here, but in my opinion, and the couple of setups that I've done, both addresses is the best option. It gives the best balance of performance and reliability. You could also pick only source address to be used for the hash, destination address, and a number of others, but both addresses seems to work well. On the Action tab, on the Extra tab, we're going to select address type not local. The mangle chain pre-routing is going to be capturing all traffic, even if that traffic is going to the router itself, that is local to the router. So to avoid this, we use address type local, and the inversion or the NOT. And the last tab, action, is mark connection, WAN 1, and we'll leave pass-through on. So we're looking at traffic that's coming in the LAN interface. We're making a decision about it to sort it into a stream using PCC, and then we're marking those connections WAN 1. We'll repeat that then 3 times because we have 3 WAN connections, and you'll notice that they come out as 3 of 0, 3 of 1, and 3 of 2. And you can copy and paste now the completed PCC mangle rules. Step 3 is create the mangles to add the routing marks to the packet. So we've marked the connections first. Now we mark the individual packets. Again, the chain is pre-routing. We're matching all packets coming in Ethernet 5. If the connection mark is WAN 1, we're going to mark routing, and the routing mark that I picked is either one-mark. And I'll tell you in a moment why I picked that particular mark. It can be anything you want. So this is where we're going to be marking routing for the bulk of our traffic that's going through the router. And we're going to repeat this 3 times, 1 for each of the WAN connections. We're also going to put some rules in the output chain. So now we're going to be looking for connection mark WAN 1 and mark routing again, either one-mark and pass through. This rule ensures that traffic from the router itself will return to the sender through the proper interface. All right, so we've repeated those route markings 3 times for the pre-routing and 3 times for the output chain. And once again, you can copy and paste and complete the setup. Step 4 is we need to identify which WAN interface the traffic came in and then mark the connections appropriately. Again, in the pre-routing chain, we're looking for traffic coming in Ethernet 1. We're using the connection mark no mark. Now, no mark is a special mark. If a packet doesn't have any mark on it, then it does have a mark, and that mark is no mark, and it's on all connections by default. So if you want to identify connections that have never been marked before, you can look for connection mark no mark. And our action is going to be new connection mark WAN 1. And so again, we'll repeat that 3 times. Once for Ethernet 1, once for Ethernet 2 as WAN 2, and once for Ethernet 3 as WAN 3. Step 4 is now complete. You can copy and paste. We have 3 connection marks. We're looking for unmarked traffic coming in the WAN interfaces and marking the connections. We're almost there. Stay with me. Final result, how do you know if your connection marks are working? Well, fortunately, under IP firewall connections, you can see all of the connections that the router knows about. And if those connections are being marked, you'll see the marks. If your PCC rules are working correctly, you should see a fairly even number of marks for each connection. So the mangles are done, now we create the routes. We'll need one default route for each routing mark corresponding to each of the WAN connections. So a default route for WAN 1, default route for WAN 2, and one for WAN 3. We'll also need one unmarked default route corresponding to each of the WAN connections. So we're going to end up with 6 default routes, 3 that are marked, WAN 1, WAN 2, WAN 3, and 3 default routes that are unmarked. So we're going to create the unmarked routes first. And if you're using DHCP client and you're receiving a default gateway, these 3 will be created for you automatically. So we're going to do them statically. So we use a destination address of all zeros and a gateway here of 172.17.01. And notice this is an unmarked default route. We'll repeat that for WAN 2 and for WAN 3. Now, the reason for this is to provide some failover, because the rule is that if you mark routes on a packet And if there is not a corresponding active route for that particular mark, then the packet goes to the main routing table. So if we're marking our packets red, but we don't have any red default routes because that connection is down, it goes to the main routing table. It goes to these routes. So even if we lose a connection and we're still marking traffic, it still has a way to get to the internet. One of the tricks that you can do here is to give one of these routes a lower administrative distance than the other. So if you've got one really reliable connection and the other two that are a bit sketchy, you can make the one with the best connection a distance of 1, the one that's not so good a distance of 2, and the worst connection a distance of 3. That way, your most reliable connection will always be favored for unmarked traffic, if it's the least likely to go down. Step 6 is create the marked default routes. Again, we can just copy the routes that we created previously with the addition of adding the routing mark. Either 1, either 2, and either 3. Now, you'll also notice that we've added one more little feature here, the check gateway feature. What the check gateway feature does is ping the gateway address and determine if it's alive. And if the gateway address is not alive and doesn't return the ping, it marks the route as disabled. The cool thing about this is that any route in the routing table, the main routing table or our either 1, either 2, either 3 routing tables, any route that references the same gateway will be disabled. So we have automatic failover. You only have to use the check gateway one time per gateway, and it will mark all the routes in the routing table with the same gateway as inactive. So here's the final result, our routing table. You'll notice a few things. First of all, every default route is duplicated. Also, each default route has a different routing mark, and only one of our unmarked default routes is active right now. The 2 that are in blue are not active. If this particular gateway goes down, then one of these guys will become active. If we give them different distances, then we can influence which one is active first, second, and third. So here's the money shot. Okay, we have it all configured. We put it into play. This is a university on the island of Hawaii. And they had 2 cable modem connections and 30 or 40 students in a computer lab. And we're getting fairly even load balancing right now. When I took the screenshot, we're at about 1.2 megs here and 3/4 of a meg here at that particular moment in time. So let's look at some common problems that people have now creating this particular setup. First of all, I use DHCP for my WAN addressing. How do I get the marked routes? Because DHCP is going to give you a default gateway, but it's not going to have a mark on it. So I realized, hey, that is a problem. We need a script. I'm not much of a scripter. So I went to my friend Andrew Cox, who lives in the land down under, and I said, Andrew, I need a script. And here it is. And you can copy and you can paste and use this script. What this script does, and you set it up on the scheduler to run every so often, is it looks at your routes, and if you don't have any marked routes, it adds them for you. So it takes, if you have 3 default routes, it will create 3 marked routes for you, and it will name them either 1-mark, either 2-mark, and either 3-mark. Or if you have a different interface name, it will be substituted for either 1, either 2, either 3. So I said before, I created my routing marks as either 1-mark. This is the reason, so they would work with this script. So here's what happens before you run the script. You just have 3 standard default routes. After you run the script, you now have 6 default routes, all marked properly. Another problem, PCC doesn't seem to work properly when I use it on the same router as hotspot and IP web proxy. Okay, It is possible to make it work. I have seen people do it. It's extremely detailed. It's very frustrating, and I really don't recommend that you try and run load balancing on the same router as hotspot or proxy. One solution I would suggest is use two routers. I mean, these things cost $50, you know, come on. Use two. One of them can do the load balancing, the other can do hotspot or web proxy. Another solution, if you just absolutely can't afford another $50 for a router, is use MetaRouter, which is MikroTik's virtual routing environment. The host router can do the heavy lifting, and the virtual router can maybe do the load balancing. Another issue I've seen, DNS resolves from some clients but not others. What's going on? Well, sometimes we might be using two different ISPs for our WAN connections, and each of them has their own name servers. Sometimes what may be happening is some clients are accessing another ISP's DNS server from a different ISP's connection. So using ISP1 name server from ISP2's connection. Some ISPs block DNS requests if they don't come from their own address space. So one solution is consider something like OpenDNS or some neutral DNS source. You can also create a destination NAT rule with an action of redirect and send all of them to your DNS cache and then point your router towards OpenDNS. Another problem, strange HTTP page loading issues. Some images load, some don't. Problems with secure sites. I've seen this happen if you try and use the classifier source address, source port, destination address, destination port. So instead of that, try something a little simpler like both addresses or source address for your classifier. Now, obviously, both addresses and ports is going to be more random than only source address and probably gives the greater chance for even distribution between your connections, but it's not worth the cost. Another problem, I can only get asymmetrical connections. I can get one DSL and one cable modem. Not a problem. You can actually weight one interface over the other and force more traffic to go through one. All you do is just repeat the PCC rule. So instead of just doing 3 of 0, 3 of 1, and 3 of 2, you can do 3 of 0, repeat it, 3 of 0, 3 of 1, 3 of 2. In this scenario, we would weight one extra stream of traffic out WAN 1. So that's it. Thank you for your time. If you want to learn more, go to mywistraining.com or learnmikrotik.com or ispsupplies.com. Also, I have the book available for sale at my table, and it's also on iTunes and Kindle. So, any questions so far?
Hi. What's the default behavior of RouterOS if I just specify different default gateways in the routing table?
Test. So what you're saying is create 2 WAN connections and 2 default gateways. Yeah. Okay.
I know it works. I just don't know what's the behavior of RouterOS, how it's choosing where to send which connection.
Yeah. Well, if you remember back a few slides, we had 2 default gateways. Okay? And because they were of equal administrative distance, one was active, one was not. So even though you have 2 default gateways, you're not doing any kind of load balancing.
So all the traffic is going through one?
Correct.
Okay.
Unless that one goes down and then the other. Right?
Thank you.
Anyone else? Pass it back maybe.
On your second to last slide, you had 4 rules of 3, 0 of 1, 0 or 3 of 1, 3 of 0, 3 of 0 twice, 3 of 1, then 3 of 2. Mm-hmm. My understanding of the way the numbering on that works is you'd want actually 4 of 0 and 4 of 1 going to the same destination, and then 4 of 2 and 4 of 3 going to the other 2 slots.
I'll buy that.
Okay, I'm not sure how the 3-way division would actually work there.
Yeah, I didn't give it a lot of thought. I know that you just simply repeat the rules so that you get more flow through one of those connections, but I didn't give enough thought to tell you whether or not that's correct. Does anybody else know? Justin?
How are you handling? I have some networks where they did the load balancing according to the wiki.
Right.
The problem is some of the traffic that they're doing this with, they can't get to from inside the network. Does your example or does your way, does that address that? Say they're inside the network, and they're on, say, their traffic is going out ISP A, but they want to get to parts of their network that's on ISP B.
Yeah. No, I totally understand. Yeah, a common problem, and that was the reason for the accept rules very early in the chain, because any traffic that should be sent out the main routing table. So just take PCC totally out of the picture. If the network works correctly, we want to make it continue to work correctly. So any traffic that should be on a directly connected network, we need to jump it out of the mangle chain, if you will. And that's what the accept rule does.
Okay, good.
Yeah. So I'm 1 for 1 on questions right now. Come on, another easy one, somebody.
In a hotspot environment, you said it's better to use 2 routers.
Mm-hmm.
So how this DHCP would be working on the main router, where we are doing the load balancing? So the first router would be the router which is getting the ISP connections. Say we are getting 3 ISP connections. The fourth
Right.
port, say we are using RB450 or 450G. The Ether 4 would go to the next router which would be running the hotspot interface.
Yeah, the question is if you're using 2 different routers because you're trying to do load balancing on one and let's say hotspot on the other, how do you set that up? It can be problematic if you can't get address space from the provider, because now you're faced with doing a double NAT. So you have a gateway router that's connected to the provider that's doing NAT. Then you have your hotspot router that's NATing a second time. Not a great scenario. What would be better is if you could get a little bit of public space from your provider. Otherwise, you're pretty much forced with doing a double NAT. And typically on a business class DSL, you can't get a /30 from each of the providers. So I think unless someone has a better solution, probably a double NAT is what you'll have to do.
So we would be getting like 2 IP address per ISP? That's what you're saying, double NATing?
No, what I'm saying, if you want to avoid double NAT, if the provider is willing to give you a public address for your public interface and then route a /30 to you, then you could take that /30 and connect it between your gateway router and your hotspot router, and then do your private addressing on the hotspot router. Again, with multiple connections, you would have to have multiple providers willing to route address space to you. That can be problematic. The other option is use private space behind the WAN, and now you have a double NAT.
In a hotspot environment, would the hotspot users see any difference if we do it or if we don't do it? As an end user, would he be seeing any difference?
No, it really, a double NAT, I mean, the main problems you have with certain protocols like voice over IP, SIP protocol, that type of thing, people browsing the web won't know the difference.
Okay, thank you.
Anybody else? There's one back there. One of my friends from Aggieland. Class of 99, represent here.
I just wanted to confirm my understanding that the reason for marking the connection is to preserve it through the load balancing process. Is that right?
Well, I think that's an accurate statement. Preserve, we're really looking at connections from 2 different aspects. One is that we want to bring the traffic back in the same interface that it went out. So from that perspective, I think preserve it is an accurate statement. From the LAN perspective, we're sorting the traffic. So, anybody else?
Thank you. In the scenario that he painted with two routers doing the load balancing, I think you don't have to do two levels of NAT there. You can route within your own network and do the NAT just at the edge.
That's a good
For
idea.
all the subnets. So that takes care of the double NAT. You have only one NAT at the edge, and then you can route within, static route within your network.
Yeah, he's
If you don't want
exactly
to do
right.
dynamic.
And giving it another 30 seconds of thought, what he's saying is that if you are using two routers, one for hotspot and one is your gateway router, then you can use public address space between the gateway router and the hotspot router. Let's say private space between the gateway router and the hotspot router, and then private space behind. You don't have to NAT. So as long as there's routing set up between the gateway router and the hotspot router, you don't need to double NAT. So thanks for clarifying.
Hi, what's the difference between setting up the load balancing this way and specifying multiple gateways on one default route?
Well, the problem with that, and I guess you're talking about like ECMP.
Yeah.
The problem with that is that I don't know what version that the Linux kernel changed in, but the table flushes every 10 minutes to help prevent denial of service attacks. And so because of that, if you have a connection open through, let's say, WAN 1, and the table flushes, then it's statistically possible the connection could be rebuilt through WAN 2. So now your connection to your banking site would be coming from a different IP address than it was anticipated coming from. So that's why this particular scheme is better in a masqueraded environment. If you're using all public addresses, then absolutely that works fine.
Okay, thank you.
Okay. Anybody else?
Let me see if I can articulate this. If one of your connections goes down, all those connection marks are still in your NAT table. Those connections, do you have to flush them out of the NAT table, or does that go away after a few minutes, or how does a failed connection help?
If you remember back to your CNA when you talked about marking packets, if there is not a corresponding route in a routing table for a particular routing mark, then that packet will follow the main routing table. So as long as you have an unmarked default route, even if a packet is marked and there's not a corresponding marked route, it goes to the main routing table. So you don't have to do anything. You can mark packets on a normal network, and if there's not a corresponding routing mark, they'll still go out the main routing table. So no intervention needed.
So if you have 3 connections and one of them goes down, you could be sending 2 times the amount of traffic out of one of the connections?
If you have 3 connections and one goes down, then you could conceivably be sending 2 times the traffic out one connection. Anybody else? I think I've taken more than my time.
I was just curious if you could use this type of setup with BGP.
Yeah, and I think I've seen some examples on the wiki, maybe. So, yeah.
Sorry?
Could get a little sketchy.
We need to repeat the question for the web listeners. No? That's okay.
Sorry, the scenario of using BGP, I do BGP with MikroTik and I'm multi-home with it, and it works perfectly well. The issue of the ECMP, where you said it drops packet, I just want to confirm, is it a standard thing that it drops packet? Because I have a network where I have 3 service providers, and I'm using ECMP there. We absolutely don't notice any problem on it, and we've been running for like 2 years. And we use ECMP. Is there a particular situation where it starts dropping the packet and you notice some problems? Because I have not noticed it, and there are no complaints on the network.
Okay, I'm not sure I got all that. Yes, sir.
Sorry, wait for it.
The loss happens if you're natting differently to each of the 3 connections in different NAT pools. So if you're not natting, then ECMP isn't going to lose the table, it isn't going to lose the translation state, and you aren't going to have a session switch from going out through this NAT to A, and all of a sudden it's going through this NAT to B, which is what causes the drops that he's talking about.
Okay, thanks. I'm not doing that, so I guess that's why I'm not experiencing it.
It's only a problem when we're masquerading. If we're using public space, not an issue. Anybody else? All right, well, thank you for not falling asleep. I know it's tough right after lunch, but and thank you for the good questions, too. If you have any more, come see me.